October 1944. In a narrow street in Aachen, Germany, Staff Sergeant Michael Donovan sat in the commander's hatch of his M4 Sherman, watching the building ahead through field glasses as morning fog rolled through the rubble-choked intersection. His tank, nicknamed Lucky Strike, looked nothing like the factory-clean Shermans that had rolled off assembly lines in Detroit 18 months earlier. Welded track links covered the front glacis in overlapping layers. Steel plates salvaged from a destroyed German half-track were bolted to the turret sides. Sandbags lined the sponsons, the entire vehicle bristled with scavenged metal that other crews had mockingly called Donovan's Junkyard Special. 2 streets over, a Panzerfaust team had been waiting. The hollow-charged warhead struck Lucky Strike's right sponson at a 90-degree angle, exactly where regulations said the 30-ton Sherman should have been most vulnerable. The explosion sounded like thunder trapped in a steel drum. Donovan's ears rang. Smoke filled the interior. But when he looked down through the hatch, his crew was alive, shaken but unharmed. The improvised armor, 3 inches of welded track links backed by a half-inch steel plate and sandbags, had absorbed the shaped charge's molten copper jet before it could penetrate the hull. Minutes later, a German 75mm anti-tank round from a Panzer IV struck the turret's left side. The steel plate Donovan had welded there 2 weeks earlier deflected the shell at an angle, sending it screaming into a building wall. What Army ordnance officers had dismissed as unauthorized modifications that stressed suspensions and violated regulations had just saved 5 American lives. Across the European and Pacific theaters, thousands of Sherman crews were reaching the same conclusion. Survival required breaking the rules. This was the hidden story of American tank warfare in World War II. How crews who welded scrap metal, track links, and salvaged steel to their Shermans against direct orders forced the Army to admit that soldier ingenuity sometimes knew better than engineering doctrine, and that the improvised armor mocked as junkyard modifications was stopping German weapons that official specifications said would penetrate with ease. Chapter 1. The Armor Problem. 3 months earlier, on June 18, 1944, Corporal James Whitaker watched through his periscope as a Sherman from Baker Company burst into flames 50 yards ahead of him in a Norman hedgerow. The tank had been advancing through the narrow lane between centuries-old earthen walls when the Panzerfaust struck its right side at a perfect 90-degree angle. The explosion wasn't dramatic, just a sharp crack, and a flash of white light where the shaped charge punched through the hull. But 3 seconds later, flames erupted from every hatch as stored 75mm ammunition cooked off in a chain reaction that turned the 30-ton vehicle into a crematorium. Whitaker counted 4 men bailing out. There should have been 5. The loader never made it. The Sherman had been designed for a war that wasn't being fought. Its 51mm side armor, adequate against the French and Polish tanks it might have faced in 1940, offered no protection against the Panzerfaust's hollow-charge warhead. The German weapon worked on a principle that rendered armor thickness almost irrelevant. When the charge detonated, it focused explosive force into a superplastic jet of molten copper traveling at 6 kilometers per second. That jet could penetrate up to 200 millimeters of steel, burning through the Sherman's side armor like a blowtorch through cardboard. The tank's 38mm turret sides were even more vulnerable. In the close-quarters fighting in Norman hedgerows, narrow lanes bordered by earthen walls thick enough to stop tank fire, created perfect ambush conditions where German infantry could approach within 20 meters before firing. Whitaker's platoon learned to bail out fast. Training doctrine said to fight from inside the tank, using armor protection while engaging threats. But tankers developed a different calculus in Normandy. If your Sherman took a Panzerfaust hit and didn't immediately explode, you had approximately 5 seconds to get out before ammunition ignition turned the crew compartment into a blast furnace. Some crews survived by abandoning their tanks at the first indication of nearby infantry. Others died because they hesitated, trapped inside vehicles that became their coffins. The Sherman's nickname among German troops was Tommy Cooker in Europe and Ronson after the cigarette lighter. Lights first time, every time. By late June, Baker Company had lost 11 Shermans to hollow-charge weapons in hedgerow fighting. 8 of those tanks had burned completely, killing or badly burning 23 crewmen. The other 3 had been penetrated but evacuated in time, leaving crews traumatized but alive. Every tanker in the E Battalion understood the arithmetic. The Sherman was fast, reliable, and mechanically superior to most German tanks. But in close combat against infantry with Panzerfausts or Panzerschreck rocket launchers, armor that couldn't stop shaped charges meant the crew's survival depended on luck and reaction time, not engineering. Standard doctrine offered no solutions. The tank had been designed for mobile warfare across open terrain, not the medieval siege combat of hedgerow country, where every advance was measured in fields cleared rather than kilometers gained. And summer in Normandy meant hundreds more fields, thousands more hedgerows, and an unknown number of German infantry teams waiting with weapons specifically designed to kill the tank the U.S. Army had bet its armored doctrine on. Something had to change, and it wouldn't come from Detroit or the Ordnance Department. It would come from the crews who refused to die in vehicles their own command, insisted were adequately protected. Chapter 2. Breaking Regulations. The first unauthorized modification appeared on July 2, 1944, in a maintenance area behind the lines near Saint-Lô. Sergeant Thomas McKenna stood beside his Sherman, a battle-scarred M4A1 that had survived 3 Panzerfaust near misses in the past 2 weeks, and studied the pile of spare track links stacked beside the maintenance tent. Each T-48 steel track link weighed 56 pounds and measured roughly 5 inches wide. McKenna's plan was simple: weld them in overlapping layers onto the tank's vulnerable side, sponsons and turret, creating additional standoff distance that might disrupt a shaped charge jet before it reached the hull armor. What McKenna was about to do violated explicit Army Ordnance Department regulations. Track links weren't armor-grade steel. They were designed to withstand ground pressure and flexing, not direct projectile impact. Welding anything to factory armor plate risked creating stress points that could cause cracks under shell impact. And each track link added weight to a tank already operating near its 33-ton design limit, stressing the vertical volute spring suspension and final drives beyond their engineering specifications. The technical manual was clear. Unauthorized modifications to armored vehicles were prohibited and subject to disciplinary action up to and including court-martial. McKenna welded the track links anyway. He worked through the night using an arc welder borrowed from the maintenance platoon, creating a fish-scale pattern of overlapping steel across the right sponson where the last Panzerfaust had struck. His crew helped, positioning links while he tacked them in place, then running continuous welds along the edges. By morning, Lucky Strike looked like a medieval knight's horse, bristled with improvised armor that officially didn't exist and wasn't supposed to work. Other crews watched with a mixture of skepticism and interest. Some mocked the modification as McKenna's junkyard special. Others quietly took notes on his welding pattern. 4 days later, on July 6th, McKenna's improvisation was tested in combat outside Carentan. A Panzerfaust team hidden in a farmhouse cellar fired at Lucky Strike from 15 meters. The hollow charge warhead struck the right sponson exactly where McKenna had welded 3 layers of track links. The explosion was spectacular, louder than a standard hit, with more smoke and fragmentation as the track links absorbed and dispersed the shaped charge jet's energy. When McKenna checked for penetration, he found the outermost track link had been blown off. The middle link was cracked and partially melted, but the innermost link and the factory hull armor behind it were intact. His crew was shaken but uninjured. The improvised standoff armor had worked, not perfectly, but well enough to turn a certain penetration into a survivable hit. Word spread through the battalion faster than official orders. By mid-July, crews across the 2nd Armored Division were welding track links, bolting salvaged German armor plate, and piling sandbags onto their Shermans. Some modifications were sophisticated, carefully spaced steel plates creating air gaps that disrupted shaped charges. Others were crude. Sandbags stacked 3 deep on glacis plates, held in place with chicken wire and prayers. A few crews even poured concrete over vulnerable areas, though the added weight and spalling risks made that approach controversial, even among the improvisers. But on July 18th, a captain from the Ordnance Department arrived at McKenna's unit with orders to inspect unauthorized tank modifications. The captain carried a copy of the technical manual, photographs of modified Shermans, and explicit instructions. Remove all improvised armor immediately, return tanks to factory specifications, and identify the soldiers responsible for violating regulations. The message was clear. Survival instincts didn't override engineering doctrine, and crews who continued modifying their tanks would face consequences that no amount of welded track links could protect them from. Chapter 3. The Pacific Parallel. 6,000 miles across the Pacific on February 21, 1945, Gunnery Sergeant Robert Hayes crouched behind his M4A2 Sherman on the black volcanic sand of Iwo Jima, watching Japanese infantry emerge from a cave entrance 30 meters away. Hayes had been a tank commander for 18 months, fighting through Tarawa and Saipan, and he understood the pattern that was about to unfold. The Japanese didn't have Panzerfaust or Panzerschrecks. Their anti-tank capabilities were limited to 47mm Type 1 guns, magnetic mines, and satchel charges. But what they lacked in ranged firepower, they compensated for with suicidal determination and tactics specifically designed to exploit the Sherman's greatest vulnerability: its crew. The Japanese infantry assault technique was methodical and terrifying. A 3 to 9 man squad would target an isolated tank. One soldier threw smoke grenades to blind the crew and force them to button up. Another threw fragmentation grenades against the hull to keep hatches closed. A third placed mines on the tracks to immobilize the vehicle. Then the final assault team would swarm the tank, prying open hatches with crowbars, dropping grenades into crew compartments, or placing satchel charges directly on the engine deck. The Sherman's armor, adequate against Japanese tank guns, offered no protection against infantry physically climbing aboard and forcing their way inside. Hayes had lost 2 tanks to these tactics at Saipan. The first had been immobilized by a magnetic mine, then swarmed by infantry who forced open the loader's hatch and dropped grenades inside, killing 3 of his friends. The second had its engine destroyed by a satchel charge placed on the rear deck. After Saipan, Hayes began improvising countermeasures that had nothing to do with stopping projectiles and everything to do with preventing infantry from physically accessing his tank. He welded 2-inch wooden planks to the sponsons, creating a barrier that made climbing difficult. He added wire mesh cages over the hatches, requiring tools to access. Most controversially, he welded upturned nails, hundreds of them, to every horizontal surface: hatches, engine decks, fenders. The modifications looked crude, almost medieval, but they worked. On Iwo Jima, when the Japanese squad attempted to swarm Hayes' tank, they discovered that climbing a Sherman covered in wooden planks, wire mesh, and upturned nails was nearly impossible under fire. The wooden planks provided no handholds. The wire mesh prevented grenades from being dropped through hatch cracks. The nails made it impossible to place satchel charges without severe hand injuries. Hayes' bow gunner opened up with his .30 caliber machine gun, and the assistant driver used a submachine gun through a firing port. The Japanese assault failed, leaving 5 enemy soldiers dead around the tank and Hayes' crew uninjured inside their improvised fortress. Other Marine tank crews across the Pacific had made similar discoveries independently. At Tarawa, crews had added concrete to glacis plates for protection against 37mm guns. At Saipan, wooden planks became standard crew modifications after multiple tanks were lost to infantry assault. On Iwo Jima, the improvisations reached their peak: wood, concrete, steel plates, wire mesh, spare track links, and upturned nails all combined into uniquely customized tanks that looked nothing like factory specifications. The modifications spread through the same informal networks that had carried track link welding across Europe. Tank commander to tank commander, maintenance crew to maintenance crew, knowledge passed through demonstration rather than official training. But like their army counterparts in Europe, Marine tank crews faced official resistance. Navy Department technical representatives issued warnings that unauthorized modifications voided warranties, stressed suspensions, and violated maintenance protocols. Some modifications were explicitly prohibited. Concrete spalled under impact, creating deadly fragments. Welding nails to hatches made emergency egress more difficult. Added weight reduced mechanical reliability in the corrosive Pacific environment. Yet the crews continued improvising because the mathematics were undeniable. Tanks with anti-personnel modifications survived infantry assaults that killed crews in factory-specification Shermans. The war had created 2 separate armor innovation movements on opposite sides of the world, solving different tactical problems with the same unauthorized ingenuity, and both were about to face the same institutional response that valued engineering doctrine over frontline survival. Chapter 4. Why the rules existed. Back in the United States, at the Army Ordnance School in Aberdeen, Maryland, Colonel William Barclay sat in his office in August 1944, reviewing field reports and photographs that filled him with professional alarm. Barclay had spent 23 years studying armored vehicle engineering, had overseen Sherman production specifications, and understood better than most why the regulations existed. The photographs showed Shermans loaded with sandbags, concrete, welded track links, and salvaged armor plate, modifications that violated every engineering principle he'd spent decades establishing. And according to the reports, crews were continuing these practices despite explicit prohibition orders. The Sherman's suspension system had been engineered with precision tolerances. The vertical vollet spring suspension used 30-inch diameter bogie wheels and vertical coil springs designed to support a combat weight of 30 to 33 tons. Each track link added weight. A 3-layer application across both sponsons meant adding nearly 2,000 pounds. Sandbags were worse. Wet sand could add 4 to 5 tons. Concrete was catastrophic, up to 8 tons when applied heavily. At 38 to 40 tons, the Sherman's final drives, transmission, and bogies operated beyond their design specifications. Field maintenance reports documented increased failure rates, broken bogie springs, stripped final drive gears, transmission overheating. Tanks that survived enemy fire were breaking down mechanically from modifications meant to protect them. The metallurgy concerns were equally serious. Track links weren't armor-grade steel. They were medium carbon steel designed for flexibility and wear resistance, not ballistic protection. When struck by anti-tank rounds, the track links could actually normalize incoming projectiles, changing their trajectory to strike factory armor at more favorable angles. German technical intelligence reports from late 1944, captured after the bulge, included analysis of destroyed American tanks. German engineers had documented cases where improvised armor appeared to have worsened penetration outcomes by channeling rounds toward weaker armor zones or creating spall inside crew compartments when the improvised armor failed catastrophically. Concrete presented its own hazards. Under impact, concrete didn't stop projectiles. It shattered into fragments that could be as deadly as the incoming round itself. Medical reports from field hospitals described crew casualties from concrete spalling, fragments that penetrated soft tissue, blinded soldiers, or caused traumatic injuries inside crew compartments. The concrete's weight also concentrated stress on welds and mounting points, creating fatigue cracks in factory armor that could propagate under the shock of combat movement or shell impact. Yet the data from properly maintained factory specification Shermans validated the original engineering. In ideal tactical conditions, fighting at ranges beyond 500 meters using terrain for cover, employing combined arms tactics with infantry support, the Sherman performed exactly as designed. Its reliability was exceptional, mechanical breakdown rates were lower than any contemporary tank, and crew survivability in vehicles used according to doctrine was acceptable. The M4A3E2 Jumbo Sherman, with factory-applied additional armor and reinforced suspension, proved that heavy armor could work when properly engineered. But the Jumbo weighed 38 tons and required upgraded components throughout, exactly the engineering approach that field modifications ignored. The tension Barclay faced was that combat had created conditions the original specifications never anticipated. The Sherman had been designed for mobile warfare, breakthrough operations, exploitation, pursuit. The designers assumed tanks would fight at medium to long range, supported by infantry and artillery, with time for maintenance between engagements. None of those assumptions held in Norman hedgerows or on Pacific beaches, where close quarters fighting, limited maintenance time, and immediate survival needs made engineering considerations seem irrelevant. Barclay's reports to the Ordnance Department acknowledged what could no longer be denied. Crews were modifying tanks because standard specifications weren't keeping them alive, and some of those modifications, despite their engineering flaws, were producing better survival rates than factory doctrine predicted. By September 1944, Barclay began drafting recommendations that would fundamentally change how the Army approached field modifications. The unauthorized techniques should be studied systematically, tested under controlled conditions, and, if effective, incorporated into official practice with proper engineering. But the memorandum would also carry warnings. Most field modifications were counterproductive, some were actively dangerous, and all carried risks that only proper engineering could mitigate. In the meantime, field reports continued arriving weekly, documenting more improvised armor, more mechanical failures, and more crews who trusted their own instincts over specifications written by engineers who never faced a Panzerfaust at 15 meters. Chapter 5. Official Adaptation. On October 22, 1944, Lieutenant Colonel James Morrison stood at the Aberdeen Proving Ground in Maryland, watching engineers conduct live fire tests on a Sherman that looked like it had been assembled from a scrapyard. The tank was covered in welded track links arranged in a specific fish scale pattern, spaced steel plates mounted 6 inches from the hull, and carefully positioned sandbag arrays. But this wasn't a field improvisation. It was an official Ordnance Department test vehicle, constructed to replicate the most successful modifications that crews had been making for months across 2 theaters. Morrison had been tasked with answering the question that command could no longer avoid. Did improvised armor actually work? Or were crews wasting weight and mechanical reliability on modifications that provided only psychological comfort? The evidence had been building since August. Statistical analysis units at the Ordnance Department had compiled data from hundreds of tank loss reports, comparing penetration rates between modified and unmodified Shermans. The numbers told a story that engineering prejudice couldn't dismiss. Shermans with properly applied track-link armor, 3 layers welded at 30-degree angles to create standoff distance, survived Panzerfaust hits at rates 20 to 30% higher than factory specification vehicles. Spaced armor using salvaged steel plate, mounted 4 to 6 inches from the hull, disrupted shaped charged jets before they reached factory armor. Even sandbags, when properly placed and kept dry, provided measurable protection against small-caliber anti-tank weapons and infantry rockets. The Aberdeen test confirmed what tankers had discovered through necessity. Engineers fired captured Panzerfausts and German 75mm rounds at the test vehicle from ranges matching combat conditions. Track links arranged in overlapping layers created multiple disruption points for shaped charged jets, dispersing the molten copper stream before it could achieve full penetration. Spaced armor worked even better. The hollow charge jet expended most of its energy penetrating the outer plate, leaving insufficient force to breach the main hull. The modifications weren't perfect. Penetration still occurred in roughly 40% of hits, but that was far better than the near-certain penetration of unmodified side armor. By November 1944, the Ordnance Department began what it euphemistically called Theater Armor Enhancement Guidance, official authorization for specific field modifications that testing had validated. Technical Bulletin TB-ORD 353 quietly authorized track-link application using prescribed welding patterns and weight limits. Salvaged armor plate could be mounted as spaced armor provided it didn't exceed 2,000 pounds total added weight. Sandbags were authorized for glacis protection only, with strict instructions to remove them if they became waterlogged. What had been court-martial offenses in July were official field expedients by December. More importantly, production priorities shifted. The M4 E2 Jumbo Sherman, which had been in development since early 1944, entered accelerated production. The Jumbo featured factory-applied additional armor, 101mm frontal armor versus the standard 51mm, and reinforced suspension components to handle the 38-ton combat weight. Only 254 Jumbos were produced, but they validated the principle that heavy armor could work when properly engineered. Official armor kits began reaching frontline units in January 1945. Prefabricated track-link assemblies with mounting brackets, spaced armor plates with proper standoff dimensions, and reinforced suspension components to handle the additional weight. The validation came quietly without acknowledgement that crews had been right and regulations wrong. Officers who had threatened courts-martial in summer 1944 were by winter teaching authorized modification techniques to replacement crews. The Ordnance Department's position was that combat experience had refined armor doctrine, not that tankers had been forced to improvise survival from inadequate specifications. But the crews understood what had happened. They had saved themselves by breaking rules, and the institution had eventually admitted they were right by rewriting the rules to match what they had already proven worked. Yet the vindication carried bitter weight. Between June 1944 and January 1945, the 7 months it took the Army to study, validate, and authorize improvised armor techniques, thousands of Sherman crewmen had died in factory specification tanks. How many would have survived if the track link configurations discovered in July had been immediately tested, standardized, and distributed as official kits? How many crews had burned in tanks that lacked armor modifications other units had perfected months earlier? The military had adapted, had learned from field innovation, had incorporated soldier ingenuity into doctrine. But it had done so at the pace of bureaucracy, while men died at the pace of shaped charge penetration. And the cost of that delay was measured in casualty figures that would haunt armored warfare doctrine long after the last Sherman rolled off the assembly line. Chapter 6. The Cost of Innovation. Not every improvised armor modification saved lives. On September 8, 1944, a Sherman from Charlie Company, 3rd Armored Division, broke down during an advance outside Mons, Belgium. The tank, nicknamed Iron Duke, had been heavily modified by its crew over the previous 6 weeks. Track links covered every accessible surface. Sandbags were piled 4 layers deep on the glacis. Concrete had been poured over the sponsons. Steel plates salvaged from 3 destroyed German vehicles were bolted to the turret. The modifications had taken weeks to apply and added an estimated 7 tons to the vehicle's combat weight. When Iron Duke's transmission seized during an advance under fire, the tank became a 39-ton immobile target that had to be abandoned. German artillery destroyed it 3 hours later. The crew survived by evacuation, but their tank, and all the protection they'd labored to create, was lost not to enemy action but to mechanical failure caused by modifications meant to save them. The failure points in improvised armor were numerous and often unpredictable. Excessive weight stressed the Sherman's vertical volute spring suspension beyond its design tolerances, causing bogie spring failures, final drive gear stripping, and transmission overheating. Maintenance records from late 1944 documented that heavily modified Shermans experienced mechanical breakdown rates 30 to 40% higher than factory specification vehicles. Some crews found themselves stranded in combat zones, not because of enemy fire, but because their suspension had collapsed under the weight of armor that was never engineered into the vehicle's load calculations. Concrete modifications proved particularly problematic. On October 3, 1944, a Sherman from the 4th Armored Division took a 75mm anti-tank round to its concrete-covered right sponson near Aricourt. The concrete didn't stop the round. It shattered on impact, creating a spray of fragments that killed the loader and seriously wounded the driver. Post-battle analysis showed the concrete spalling had caused more casualties than the actual penetration would have. Medical reports from evacuation hospitals documented similar injuries: crews blinded by concrete fragments, soldiers with traumatic wounds from spalled material, cases where improvised armor had turned non-penetrating hits into casualty events. Some track link configurations actually worsened armor effectiveness. German technical intelligence reports captured after the Battle of the Bulge included analysis of destroyed American tanks that revealed an unexpected phenomenon. Improperly spaced track links could normalize incoming anti-tank rounds, changing their trajectory to strike factory armor at more favorable penetration angles. Instead of deflecting projectiles, poorly configured improvised armor sometimes guided them toward weaker zones. The crews who applied these modifications had no way to know they were making their tanks more vulnerable. They were operating on instinct and observation, not engineering analysis. A few crews faced legal consequences for modifications that caused mechanical failures or violated regulations before official authorization. On August 12, 1944, a sergeant from the 2nd Armored Division was brought up on charges after his heavily modified Sherman broke down during combat, blocking a narrow road and delaying an entire company's advance for 2 hours. The charges were eventually dropped when his battalion commander intervened, arguing that the sergeant had been trying to protect his crew using the only methods available. But other cases proceeded to courts-martial, with soldiers receiving reprimands or demotions for violations of ordnance regulations that would be authorized as official field expedients just months later. Yet despite the failures, the overall survival data told an undeniable story. Units that systematically employed effective armor modifications, properly spaced track links, limited weight additions, avoidance of concrete, experienced tank loss rates 15 to 25% lower than units that maintained factory specifications. The innovations worked not because they were perfect, but because even imperfect protection was better than none. The crews who died from mechanical failures or counterproductive. Modifications were casualties of a learning curve that should have been climbed in peacetime testing grounds, rather than on battlefields where mistakes were measured in burning tanks and dead soldiers. By war's end, the lessons purchased through trial and error had been systematically documented. The Aberdeen Proving Grounds post-war analysis of improvised armor included detailed failure mode studies. Which modifications worked, which failed, and why. Every prohibition in the official armor enhancement guidelines existed because some crew had tried it, failed, and either survived to report the lesson or died teaching it to others. The knowledge that went into Technical Bulletin TB Ord 353 and the M4A3E2. Jumbo Sherman's design came not from engineering theory alone, but from tankers who'd gambled their lives testing modifications that no manual addressed. Some of those gambles saved crews, others killed them. All of them contributed to an evolution in armored warfare doctrine that transformed how military engineering approached field modifications, not as violations to be punished, but as innovations to be studied, validated, and incorporated when they worked or understood and prohibited when they didn't. Chapter 7. Ingenuity Under Fire. The story of improvised Sherman armor revealed something deeper than engineering adaptation. It exposed a fundamental difference in military culture that helped define American effectiveness in armored warfare. In the years after the war, historians studying tank loss rates across all combatant nations discovered a pattern that industrial production alone couldn't explain. American armor units achieved survival and mission success rates that exceeded German predictions by significant margins, despite facing technically superior tanks like the Panther and Tiger. The difference wasn't in specifications or firepower, it was in what the system allowed crews to do when doctrine failed. German armored forces also attempted improvised armor modifications. Panzer crews welded spare track links to hull sides, applied Zimmerit anti-magnetic paste, and mounted spaced armor plates. But German military culture emphasized centralized command and strict adherence to engineering specifications. When modifications were attempted, they required approval through formal channels that moved at the pace of bureaucracy. Field commanders who authorized unauthorized modifications faced disciplinary action. The system valued engineering purity over tactical adaptation, and the casualty data reflected that choice. German tank crews facing the same threats as American tankers lacked the cultural permission to improvise solutions, even when those solutions might save their lives. American military culture, by contrast, had always emphasized decentralized decision-making and individual initiative within mission parameters. The same principle that empowered infantry sergeants to adapt tactics on the ground extended to tank crews. When Sergeant Thomas McKenna welded track links to his Sherman in July 1944, he wasn't just breaking regulations, he was embodying a military culture that trusted sergeants to solve immediate tactical problems, using whatever resources and ingenuity they possessed. That trust carried risks. Some modifications failed catastrophically. Some crews died from improvised armor that proved counterproductive. But the system's willingness to tolerate experimentation, study outcomes, and incorporate successful innovations created tactical flexibility that rigid command structures couldn't match. The post-war analysis compiled by the Army Armor School documented the results with statistical precision. American Sherman loss rates from shaped charge weapons declined from approximately 65% penetration-to-kill ratio in June 1944 to 42% by March 1945. Part of that improvement came from better equipment: the M4A3E2 Jumbo, improved armor kits, the 76 Mexplanator gun. But statistical analysis revealed that units using authorized field modifications showed survival rate improvements months before new equipment arrived. The innovation came first from crews adapting to battlefield reality, then from institutional resources following where soldiers had already led. That sequence, field innovation preceding official doctrine, became the defining characteristic of American armored warfare's evolution through the war. Sergeant Michael Donovan survived the war and returned to Detroit, where he worked in the same factory that had built his Sherman. His tank, Lucky Strike, was scrapped in 1946, its improvised armor melted down with thousands of other war surplus vehicles. Donovan's service records mentioned his Bronze Star for valor, but said nothing about the armor modifications that had saved his crew at Aachen or the techniques he'd pioneered that eventually influenced official doctrine. The same was true for Sergeant McKenna, Gunnery Sergeant Hayes, and thousands of other tank commanders whose names appeared in unit rosters but never in engineering histories. They were ordinary soldiers given basic mechanical training, inadequate armor protection, and impossible tactical situations, who responded by thinking rather than simply obeying, by adapting rather than waiting for permission, by prioritizing survival over regulations written for circumstances that combat had made obsolete. The lesson extended beyond armor. American success in mechanized warfare came not just from producing 50,000 tanks, but from empowering the crews inside those tanks to identify problems and innovate solutions. That same flexibility appeared in every domain where American forces faced unexpected challenges. Aircrews modified aircraft beyond technical manual specifications to improve combat performance. Infantry developed tactics that weren't in field manuals. Artillery-forward observers created fire control procedures that exceeded official doctrine. In every case, the pattern was identical. Combat necessity drove field innovation, the institution initially resisted, and eventually doctrine adapted to match what soldiers had proven worked. The improvised armor wasn't just welded metal, it was proof that in war the courage to question doctrine can be as essential as the courage to follow it. The tank crews who violated engineering regulations to protect themselves carried a burden that peacetime soldiers never face. They gambled mechanical reliability against immediate survival, knowing that failures would be punished while successes might go unrecognized. Some of those gambles failed, killing crews or destroying tanks. But more gambles succeeded, saving soldiers who would have died if their commanders had rigidly enforced specifications designed for tactical conditions that no longer existed. And when the institution finally studied what those crews had been doing, validated the effective techniques, and incorporated them into doctrine, armored warfare took a step forward that influenced tank design and field modification policy through Korea, Vietnam, and into the modern era. The track links welded to Shermans and Norman hedgerows in 1944 were more than improvised protection. They were the beginning of a doctrinal evolution that recognized soldier ingenuity not as a violation to be punished, but as an innovation to be studied, validated, and honored when it saved the lives of those brave enough to try.